My name is Gaurav, and I will be teaching the reinforcement learning aspect of the course. I'm a scientist at IBM Research, and I also taught the reinforcement learning aspect last year. And today there will be in this year I will add some more on top of what I covered last year. But I will also cover the basics, but I'm not assuming any reinforcement learning knowledge. Okay, first of all, Professor Tanmoy has already covered instruction tuning. So why is instruction tuning not enough? Why do we need something more? So let's say you want to teach the model to follow a particular instruction given an input. You could just give the input and the output and just train it just like you do supervised tuning, right? But sometimes it is not enough. And the reason is that when you do instruction tuning, you tell the model what to do, right? You give the input, you give the correct output, but you never tell it what not to do. Let's say the model, you gave it, let's say example, so here the example is, what is the best way to lose weight quickly? And now you gave the model the correct example that, okay, if you reduce carb intake, increase fiber, protein content, blah, blah, that should help. But along with this response, the model have learned some other responses during its pre-training. It has seen a huge amount of corpus during its pre-training, and we don't know what all it has learned. So you're not telling it what it has learned, and whatever wrong that it has learned, its probability should be reduced. And that's where alignment comes into the picture. It not only allows you to increase the probability of certain output, it allows you to decrease the probability of other outputs. There are two ways to classify alignment methods. There are multiple ways. I have shown here two ways to classify alignment methods. First one is based on the objective that you are concerned with. So whether you are interested in maximizing the reward, where we'll talk about where the reward comes from, or it might be the case that you want to somehow contrast between good outputs and bad outputs, right? And you don't have a reward function as such. And the third one, which we'll not cover, is where we use distribution matching where we have some target distribution that we want to reach, and then we use some distribution matching approaches so that our model starts behaving like the target distribution. So that is the classification if you based on the objective that you're trying to align with. The second classification is whether you want to do this training of the model, whether you want to do this alignment in an online fashion or an offline fashion, or a hybrid between the two. So what I mean by online? Online means that you have a model, you have the model that you care about, and you want to improve it, you want to train it, but you want to train it using its own sample as the model evolves. So that is called online training. And the offline training is that samples, before you start the training, you get the samples or the outputs beforehand from there. And those outputs can come from the model, those outputs can come from somewhere else. And then you use those outputs, you convert them into either preference pairs, or you convert them into whatever format you want. And you train the model on those output pairs that you have gotten beforehand. So that is offline. And then there are also mixed approaches, which sample some outputs, do some training, again sample outputs, do some training. And most of the approaches use some form of mixed training, as we will see later. Okay, so before I talk about reward modeling, I will cover the basics of reinforcement learning, since I'm not assuming any familiarity with this topic. Okay, so when I say reinforcement learning, what I mean is that you have an agent which acts on an environment, takes some action in the environment, gets a reward, and then based on because of the action that it took, its state changes, and it again takes an action, again gets a reward, state changes, and this loop keeps repeating. So what is agent? So these terms are very vague, right? What is agent? What is environment? Uh, so let's make them more concrete. So environment is the space where everything that the agent has to be concerned with. So let's look at an example of where we are interested in creating an AI based chess player. It's a program that can play chess using artificial intelligence, let's say. Here the agent is the AI program that will move the pieces on that will decide what the pieces to move on the chessboard. The environment is everything that agent has to be concerned with. So the environment here would be not only the chessboard, but the opponent here, the brain of the opponent, everything. I mean, so it does not have to be something that the agent can observe. It's anything that can influence the next state. And if you're playing chess with somebody, obviously the person's opposite you, that person's brain can affect the chessboard, right? And then the rules of the game, right? Now, state is like a snapshot of the environment. The state is, or more accurate, its state is the information of the environment that is available to the agent. So, in the case of chess, you cannot see what the brain of the other player is doing, but what you can see is the moves that the other player is making, and based on that, you can try to guess that maybe this player is trying to checkmate me or whatever, right? So the state is the historical position of the pieces, the current position of the pieces, all that information comes into the state. And the rules are assumed to be anyway part of the state. They are always there, right? And your action in the case of chess is simply to move a piece. And once the game is over, you get a reward of +1 -1. So reward is something that you can get after every action, or you may get at the end of the game, or you may get at some intermediate step. Reward does not there's no condition on the reward that it has to you have to get the reward every time step. So if you don't get the reward, you can assume the reward to be 0 at any time step. So again, and to environment is something that provides you the next state. Given one state, it provides you the next state, and it also gives you a reward for the action that you took from the state, right? Another example is that of a self-driving car. So in self-driving car, your agent is the AI program that will decide where the car should move, whether it should accelerate, decelerate, and all those stuff. And the environment is all the entire, basically this is the real environment, right? The road, the pedestrians, the other cars, everything that this car that the AI is driving has to interact with, everything is the environment. State is again the part of the environment that can be accessed by you, because you cannot guess what the pedestrians are going to do. You cannot guess what is going on in the mind of the other car drivers. But what you can guess, what you can see is what your sensors in the car can tell you. So it's not only the current sensor readings, but all the historical sensor reading as well. And your actions are, you can either turn, you can accelerate, brake, the multiple choice of actions that a self-driving car can have. And then you may get a reward at the end, or you may get a reward at intermediate time step also for doing the executions correctly. I have not talked about policy much in this too. Policy is, you're an agent and you have to take an action. So where does the action come from? So policy is something, it's a distribution. It can be a probability distribution over the actions that the agent will take, or it can be some deterministic function that takes the current state and gives you an action. So it's basically something that will tell you what the next action is going to be. The third example is what we are concerned with, which is that of an LLM. And here in the case of an LLM, the states are pretty simple. The state is basically whatever tokens are there in the prompt or input or instruction, and whatever tokens that you have generated so far. So this is one special example of LLM in reinforcement learning. Here the actions are just individual tokens. Your states is the input instruction prompt and whatever you have generated so far. And your environment is very simple. So environment, again, remember, environment is something that has to tell you what the next state is going to be. and it has to tell you what the reward is going to look like, right? So here the environment is pretty simple because the state is just the tokens so far. Once you take an action, what would be the next state? If you think about it, since the state is just the tokens and you have taken one action, an action is a token basically. So what would the next state be? Yes, it will just append the next token to your previous state. So environment is not doing much here because the LLM is basically, because we have created this spatial scenario of LLM, which is where the environment does not have much scope to do anything. We'll look at a more interesting example in the next slide. And the reward generally you will get once you have generated the entire response, and then based on the correctness of the response, you will get a +1 or a -1. So fourth example is also of an LLM, but here the action is not a single token. Here your agent is again an LLM, and there are only two possible groups of states. One where you have only seen the prompt or the instruction or the input. I'm using the word prompt, instruction, and input in an interchangeable fashion. And the second group of state is where you have the prompt and the response. So there are only two groups of states here, right? You will see that there is no cycle here. That's why. And the action is the entire response that your LLM will generate. And you get a reward of +1 if the response is correct, and you get a reward of -1 if the response is wrong, same as in the previous case. The difference is that instead of having tokens as actions, we have the entire response as an action. So this is not a very interesting, from an RL perspective, it's a one step RL. There is not much of RL going on here. It's just like one step that you take, get the reward, and train. The last example, which is more interesting, is a code LLM. So here the task is that the LLM has to generate a code for a given task, let's say. Okay, the task can be simple, like write a program for sorting a bunch of numbers. And the environment is a unit test framework. What I mean by unit test framework, that you have a bunch of unit tests, you have the code that is generated, you run the unit tests on the code, and it will tell you whether the assertions passed or the assertions failed, basically whether the code executed correctly or not. So the state is your problem description, the code that is generated, all the code that was generated previously also, and any error reported by the unit test framework. So you might get an exception when you execute the code, right? So all that information is your state, and based on the state, you can again generate a new code, which will again get passed through the unit test framework. Again, you will get some exception, or you might get that the code executed correctly, and this will keep on repeating, and then you get a reward of +1 or -1. So yeah. Okay, so these were 5 examples that we saw. Now let's move towards the third example that we saw, where the actions were tokens, and the environment just appended the token at the end of previous tokens. Okay, so tokens as actions, that's the special part of this reinforcement learning. So the policy, we have talked about that agent takes an action, but where does the action come from? So in the case of a language model, the actions comes from a probability distribution that the agent has, and that probability distribution is the probability distribution that your LLM encodes, right? An LLM corresponds to a distribution over tokens at every time step, right? So pi theta is the distribution that the LLM of the LLM. ST, the state, is, we have discussed already, it's the tokens of the input plus whatever output tokens have been generated so far. And the action can be any token from the vocabulary, right? And what the policy does, policy is just a distribution over the actions or the tokens of the vocabulary. So your policy takes an action 80, and in the case of an LLM, so the language model that you see on the right, the state that it receives is basically the prompt and the tokens that it has generated, which is ST, and the LLM policy represents a distribution over the output tokens. You sample a token from the policy. Let's say the previous token was Taj Mahal, and the next token is the action. Then is basically the action taken here. This is pretty simple. I hope there is no confusion here. Right. Okay. Now, as I mentioned earlier, that environment simply will take the token that you have generated and it will just append the token to the previous tokens. And if end of text has been generated, you will also get a reward based on the correctness of the response. For now, we can think that there is a human looking at the entire response and then finally giving a reward. And we will see in reality what happens. Yeah. And if end of text has not been generated, you may not get any reward, right? And the state change is simply the addition of the new token. So this is what it looks like, a typical policy taking actions. So if it is a LLM and the policy is pi theta, it takes an action in the environment, its state changes, it gets a reward, it again takes another action, and it keeps on doing that until, in the case of a language model, until the end of text is generated. And again, the next few slides are just taking showing the LLM policy as an example. In the first token, let's say the Taj was generated when you gave the prompt only as input, and you did not get any reward because the response has not completed. In the next token, condition on the Taj Mahal is generated. Again, you did not get any reward because end of text has not been received. In the next step, the next third token is generated and there is no reward. And let's say after all the tokens have been generated, there was an end of text and you get a reward. So this is how the LLM policy generates actions step by step and it gets a reward. So this was just to familiarize you guys with the LLMs, how it works as a policy and how it fits into the reinforcement learning framework. Okay. So now we'll talk about the reward model. So we have so far what we have said is that when LLM the policy execute, it may or may not get a reward. But who is giving this reward, right? We said that okay, human might be looking at the response and giving a reward every time. But this is going to be very expensive, right? So we can ask humans to give thumbs up or thumbs down to every response that the LLM generates. But this thumbs up, thumbs down for humans is going to be very expensive. And if we are doing this in a training framework, this will take forever. And we will see that when we do traditional RLHF like PPO, it's a non-policy method. So as you train the model, you need new feedback, and you train it again, and you have to keep on getting feedback. So obviously, humans are out of the picture. So the simple solution is that let's train another language model to mimic what a human does, right? So how do you do that? We'll look at how we can train an LLM to behave like, instead of saying reward model, I should say, okay, behave like humans, right? And in some cases, there are some cases where the answer can be verified exactly. So you actually don't need a reward model in some cases. Can you think of some scenarios where you don't need a reward model to tell you if something is generated correct or not? Mathematical questions. So if you have the ground truth available in mathematical questions, let's say you have the final answer that somehow there was a problem and the final answer you have supposed to reach is 23. Now you can still reach 23 by doing all the wrong reasoning, but that chance is low, right? So there is, if the model generated some solution and finally reached the number 23, it's quite likely that it must have followed a correct chain of steps to reach the 23. So in those kind of scenarios, you don't need a reward model, and you can just use the ground truth to verify the correctness. So those situations fall under verifiable rewards, and verifiable rewards are the best. If you can find a verifiable reward for your task, that is the best thing you can do. Why? The reason is that whatever reward model you train, they are going to be be biased, they are going to be noisy, and when you do training with those noisy biased reward models, the model will learn some spurious signal that you don't want. So if you can find a verifiable reward for your task, that is the best thing. So in maths, exact numerical answer match is a good signal for training, and it's something that all the works, including Grok, ChatGPT, and whatever models anybody is training for maths, all of them use exact numerical answer match to do reinforcement learning for maths. Similarly, for code, if you have unit tests for that your resultant code should pass, which generally we have, right? In a lot of cases, we do know that final code that we get should take this input and return this output. So if you have the unit tests, then again what you can do with code is that whatever model generates, you can run those unit tests on those code and then give the reward based on the correctness, right? In case of question answering, especially factual question answering, you can match. Like if our question is that where is Taj Mahal, then if the Agra word comes into the response, then it's very likely correct. So you can do simple string matching. Similarly, for if you are training a model to generate a sequence of steps for solving or generate a proof basically, then you can use automatic proof checkers to verify that whether the steps of the proof follow from each other or not. So it might not be a complete signal, but it will give you a partial signal that at least the steps are follow from each other, and it's not hallucinating some random steps. In chemistry, if you know that what the output of the reaction can be, then you can just match those outputs. And similarly, in protein structure prediction, if you know what is some cases where the protein structure, some information about the angles, whatever information you have about the structure, if you can match that with whatever the model outputs and get another signal. So there are a bunch of signals all over different fields that can be used as verifiable reward. And the good news is that these verifiable rewards don't depend on the human preferences, which can be noisy, and they are often incomplete, right? You cannot get the labels for all possible preference pairs from humans, right? And by using verifiable rewards, for example, Grok 4 has been able to achieve very high scores on a bunch of different benchmarks. So it has become very trendy nowadays, at least. Okay, so this was the case where you don't need to worry about reward models. But in let's say you are doing essay writing, right? And you want to train the language model to be able to write very good essays. So in such a case, even if you have the ground truth perfect essay that you have, you cannot match it to whatever the LLM generates, right? Because the format might be different, the style might be different, the content might be different. I mean, if you're writing an essay on cow, there are 100 ways, and none of them are going to be very similar to each other, right? So in those cases, verifiable rewards don't work, and there you actually need to train a reward model to be able to tell you whether whatever was generated is good or not. And what is a reward model? It's basically an LLM which takes your task, your prompt as input. It takes whatever the language model generated as one of the inputs, and it gives you a score. And the only criteria is that this score should be high if the output was correct, and it should be low if the output was wrong, right? That's what you want to train it on. Now, who decides correct and wrong, right? So here we are saying that it's desirable that the reward of the better response should be higher than the reward of the not so good response. But who decides what is better? So we have to somehow get that information also. If it is decided by humans, then the entire RL framework falls into RLHF. And if it is decided by AI, we call it as RLAIF. But people tend to use these two terms interchangeably. So especially RLAIF, RLHF, AIF is often also referred to as RLHF. So, but you don't have to worry about this. Also, if there is a verifier, like we saw in the previous case, right? Then this framework is called RLVF, reinforcement learning with verifiable feedback. So this is how a typical reward model looks like. It's a language model, and what it takes as input, the instruction, the prompt, and the response generated from the LLM, let's say, right? And you now this LLM can be encoder. The reward model can be an encoder only model. It can be a decoder only model. It can also be an encoder decoder model. You can think of whatever scenarios are possible. Ultimately, what you care about is the pre-logit layer. What is the pre-logit layer? So the logit layer is that after you apply the vocabulary mapping, whatever scores that you get is the logit layer. So before the vocabulary mapping layer, the embeddings, d-dimensional embeddings that you get before you apply the vocabulary mapping to get the final token distribution. So that embeddings are called the pre-logit embeddings. And on top of those pre-logit embeddings, you can do a bunch of stuff on top of those pre-logit embeddings. You can average all those pre-logit embeddings and then apply a linear layer and get one single number as output. That is one way. Or you can take the last token. If you are working with the decoder only model, you can also take just the embedding of the last token, apply a linear layer, and get another number as output. So this part is quite, there's no fixed way. Okay. So again, the architecture is very simple. Now we'll talk about how to train this reward model, which is more interesting. So the preferences are binary. Let's assume that the preferences are binary, and the way we got those preferences was, I don't know if okay, yeah, we'll talk about later. And the way we got those preferences was, let's say we showed two outputs to a human being and asked them to pick which is better, and that's how we got the preferences. Okay, and now we want to fit a statistical model to these preferences. Okay, so the Bradley-Terry model is a statistical model that can fit to binary preferences. If you the word statistical model is confusing, then statistical model is basically if you, let's say, toss a coin bunch of times, then we know that the Bernoulli model or the binomial model can be used depending on the task. Similarly, the Bradley-Terry preference model is just a statistical model that can fit if you have a bunch of preferences. So to understand it, let's say you have n items, and you have for each of the item you have a score pi. Let's say the item yi has a score of pi. So the Bradley-Terry model is defined. This is the definition. So what it says is that if you have a bunch of items and their corresponding scores, the probability of picking item I over item j is defined as follows: probability yi, and I say this symbol that I write, this means preferred over. Yi is preferred over yj. This is defined as pi. Let me put this pi plus pj. So this is a definition of the Bradley-Terry model. Okay, and if we assume that all these scores are positive, then I can write these scores pi as exponential of some theta I, where theta I is trainable. So generally, how the data will look like, you won't be given these scores P1 to Pn. These are the parameters that you have to estimate. And when you are fitting a predictory model, all you will be given are preference pairs. So you will be given y1 is better than y2, y2 is better than y3. Those kind of preferences is what you will be given. And your task will be to learn. These are the pi and pj are the parameters. Your task will be to learn these pis and pjs that would fit to the preferences. So this is the general predictory model. Now we'll talk about the special case in LLMs. So for LLMs, in language models, you not only have those yi and yj, you also have prompt, the x as input, right? So so here you define the conditional distribution of picking yi over yj given an input prompt. So probability of picking yi over yj given a prompt x. This is what you define, and this looks like so again p y. Actually, this can be any score, but I'm using the term pyi given x. This py, instead of pyi given x, you can actually use whatever score function you want. And so these are the quantities that you want to train. These are trainable quantities. So first thing is you parameterize this thing. The parameterize the quantities using a LLM. So LLM takes x and yi as input and gives you. So actually, let's the way I can parameterize this pyi given x as, let's say, so these are not probability, these can be anything, and you can parameterize them as exponentiated r theta x comma y. It's a r theta is a neural network which takes your prompt and it takes your output yi as input and it generates some score as output. So and this is what you want to train this neural network, right? So if you parameterize your predictory model using this LLM, the probability of preferring yi over yj can be written as so if you're given preferences, you can parameterize your predictory model using a LLM and then train the predictory model, basically get the parameters to maximize the likelihood of observing whatever data is. So yeah, so we'll talk about how to do maximum likelihood estimation in the case of a predictory model. Okay, so let's say you have data of the form x, y plus, y minus. Y plus is your preferred output, y minus is the unpreferred output, and you want to find the optimal reward model r theta star to maximize what the log probability of the all the preferences that you observe. So how will you do it? So again, just like you would fit a statistical model to Gaussian data, you will similarly fit a statistical model to preference data. So what you do is you will first define your likelihood function. What is your likelihood? L theta. So for one triplet, what will be the likelihood? Let's write that, and then we will write the likelihood for the entire data set. So if you are given only one triplet under the predictory model, what is the likelihood? It's log probability of preferring yi greater than yj, yi over yj. Sorry, not y over yj given x, and which I can write as log exponentiated r theta x y I. I should not have this. So I can write this Bradley-Terry likelihood for a given triplet as follows. And since we have an entire data set, we will take the expectation over the data set. So expectation over these triplets coming from the data distribution coming from this quantity, and this again is going to be plus, and this is going to be minus. Right, and similarly this also will be this expectation x y plus y minus coming from the data distribution. So this is how your log likelihood of the preference pairs look like, and you can do this shuffling here and there, and what you get is a very simple looking nice form. Log sigmoid r theta minus r theta of the on the rejected response. Okay. So what is this likelihood saying? It's simply saying that the reward of the preferred, this is the reward of the preferred response y plus, maximize this quantity and reduce the reward of the unpreferred response. So basically try to maximize the difference between the preferred response and the rejected response. That's all this likelihood is trying to do. Right, so that's this is how you can, the expectation you can just, because this distribution is a discrete distribution, you can just write this expectation as an average. And what this quantity is saying, this is the reward of the preferred response, and this is the reward of the rejected response. And it's just trying to maximize the difference of the reward between these two responses. You're asking that how does sigma come from this equation, or so this is an exponential, right? So if you subtract r theta y minus or multiply by exponential minus r theta y x y minus both sides, you'll get a sigmoid form. So this this quantity that you see here, this is sigmoid. Yeah. Okay. But from another point of view, that why do we use sigmoid here? That's the reason is that you don't want it to become unbounded, and that's why the sigmoid comes into the picture. Okay, so now we know how to train the reward model, and I am guessing it's a very simple function. Just like for supervised tuning, you write the log likelihood and you just differentiate and let it train. So similarly, for training a reward model, you write this function that takes pi plus y minus, compute the difference, and let it train. So it's as simple as doing training any other function that you have. Okay, so now that you know how to train from the preference data, where do you get this data from? So there are some preference data that are publicly available. We'll talk about two here and one more in the later slides. There is this data from OpenAI which for doing summarization, text summarization, and here the prompt is very simple. Prompt is summarize the following document, and then you're given document. And the outputs are generated by the models that OpenAI has, the Instruct GPT models. These are older models. And the preferences are generated by humans actually. So these are human generated preferences. And then there's this ultra feedback dataset where the prompts cover not just summarization but a huge variety of tasks. These are, I think, these prompts come from a wide variety of tasks from different instruction tuning datasets. And the outputs are generated from again a wide variety of models from the GPT family, the Llama family, Bard, Wizard LM, Alpaca, a bunch of different models. And the preferences are generated by GPT-4. So you can directly take these datasets and define your log likelihood function and train you on top of this. But if you, let's say there are some cases where you don't have publicly available preference data. So where do you get the prompts from? Where do you get the responses from? And where do you get the preferences from? So the prompts you can, let's say if you have some instruction tuning data for your task. You don't have preference data, but maybe you have some data of the form question answer or input output. If you have those kind of data, so you can pick those prompts and you can get the outputs again from all the language models, Quen or Bard or Alpaca or ChatGPT or whatever models that interesting to you. And to collect the preferences, you can directly collect the preferences by showing those outputs to human and ask them to pick which is better. Or you can use LLM as a judge to decide which output is better. We'll see examples of LLM as a judge in the later slides. But these are two different ways to collect preferences. So the approach used by constitutional AI for collecting harmlessness preferences was somewhat interesting when this paper came out. Because till now, at that time, the way people were collecting preferences by showing the outputs to the model, just asking which is better. So constitutional AI, the team at Anthropic decided that, okay, let's put some principles in place. Is this response less, more wise, ethical, polite? So they created 16 principles altogether. And they would take one principle and they would show it to the judge model, whatever language model they are using for judging. And they would say the principle will look like that: choose the response that is wise, ethical, polite, and friendly. For example, this is one principle. And the input to the language model will contain the conversation, the multiple choice, the multiple possible responses, and then the principle. And the LLM has to pick which response is better according to the principle. Okay.
In this,
yeah.
In the approach, we've been asking some words randomly so that like the judge model doesn't get biased on certain output corresponding to some random distribution. Instead, we are asking some certain words, and then we are saying the judge model to predict which response is better and more aligned towards certain perspective.
So masking is likely.
We are giving clues to the model, not exact answer.
Yeah, I mean, instead of masking, maybe you can do rephrasing. Like whatever the response are, you can rephrase both the response using different models. So that, let's say, if a model is more biased towards, let's say, ChatGPT is more biased towards responses that come from ChatGPT. So in which case, if you rephrase the responses using, let's say, Claude, then it's likely that ChatGPT that bias will get away from the picture. Masking also might work, but I'm not sure 100% that with how effective masking is. Maybe the masking will confuse the model altogether. Okay, so this we talked about a Bradley-Terry preference model, but there are other preference models that are not Bradley-Terry. So we'll look at some of these models. So before that, let's talk about this help steer data. So when NVIDIA was trying to train a reward model, they realized that whatever reward model they train, these reward models tend to be biased towards longer responses. And this the reason for this is that the humans' preferences tend to be biased. That's, in general, humans prefer longer responses than shorter responses because their longer responses are generally more informative, so they prefer longer. But the models don't pick that the fact that these responses are picked because of informativeness. They pick the fact that these responses are picked because of length, because length is a very easy signal to overfit on. So what they did, they decided that okay, since it's picking signal, this spurious signal, let's make these responses, let's make these annotations more informative. How do you make the annotation more informative? Instead of asking the humans to say which response is more preferable, what they did was they showed only one response to the human instead of two responses. And then they asked the human, the annotator to basically give a score per attribute for the response. So they had 5 attributes: helpfulness, correctness, coherence, complexity, and verbosity. And they asked the annotator to give a score between 1 to 5 for each of those attributes. And you can see that these attributes on the right hand side, these attributes are not like verbosity is not correlated with helpfulness. That means even small responses can be actually very helpful, but the model does not learn that. If the model is trained from preferences, it will learn that longer responses are more helpful. Okay, so this is the data that they got. They got a vector of scores instead of just single preference. They got a vector of scores per response. And now, what do you do with this vector of scores? How do you train a reward model? So you cannot use a Bradley-Terry preference model now because you don't know which is preferred. So what they did was they converted that score vector into a string. So let's say you have the helpfulness of 2, correctness of 3, coherence of 4, complexity of 1, verbosity of 2. They will convert all of this into a single string. And then the language model was trained to predict this string given the response and the prompt. So instead of predicting which response is preferable, now they will predict an entire string of scores, and then this string of scores is used for training the LLM. We'll see how it is used later, but the point is that instead of training a reward model, Bradley-Terry reward model, you can train a preference model. Another reward model that people have used and it has become more popular recently is the LLM as a judge, but with some additions that we'll talk about later. So LLM as judge is very simple. Let's say you want to do pairwise compare. You want to get pairwise preferences from the judge model. What you will do is you will take the input, take the multiple outputs, 2 outputs that you have, show it to the judge model and ask it that pick the better response, and also give a reasoning why this is better, right? And generally you have to, if you don't ask to give reasoning, model's performance is worse, is not as good. And but if you ask it to give the reasoning first and then pick, then the reasoning helps the model decides which response is better. Similarly, if you want to get the score of a single response, you will just give the single response and ask the LLM to give a score. Also, you can do reference guided grading where you actually give the ground truth response and say, okay, this is the ground truth. Now tell me how good this generated response is. Okay. The advantage of judge models are that they can be used out of the box. They don't need any preference data. But the disadvantage is that you're not using and also, so another advantage is that you can use the reasoning capability to arrive at the final answer, right, of the LLM, because the LLM has been trained on so much text and they are very good at reasoning. You can use that reasoning to arrive at the final answer. Reward model cannot have any reasoning, right? The Bradley-Terry reward models. But the disadvantage is that they are not as accurate as reward models trained on preference data. The reward models that have seen the preference data, the judges have never seen this data, so they are not accurate, and we will see how to fix it in the next slide. Also, these are often overconfident. So what I mean is that if you ask that is this response correct, the model will say yeah, it's perfect. I mean, the models have will often agree with whatever you show to them, so they're not very, they're pretty biased. And also they like longer responses, but which is true of general reward models also. Even Bradley Tay reward models like longer responses. So can we do better than this? Can we somehow take these LLM results and make them better than the Bradley Tay reward models? Because then we will be able to use the reasoning of these models also. Okay, so these are some examples of how to use LLM as a judge for pairwise comparison. So here you give the prompt, you give the question, you give two possible answers, and then ask the model to pick which is better. This is the prompt. If you want to do single answer grading, you will just give a single answer and ask the model to give a rating between 1 to 10, let's say. Okay, so we mentioned that you can train the judges also. I mean, you can train the judges somehow to make them better than the Bradley Tay reward models, right? So one simple thing is, you take those judge models and you give the prompt, give the response, and ask a simple question: is this response correct? And if the response that you gave was actually correct, you maximize the probability of generating the token yes. And if the response was wrong, you maximize the probability of generating the response token no. So this is a very simple scenario, that you took a judge model and simply maximize the probability of generating yes or no. So yeah, so if the solution is correct, maximize the probability of saying yes. If the solution is wrong, maximize the probability of saying no. And during inference, what you will do is, you will simply look at the probability of the token yes and say, oh, this is my score. Whatever the log probability of the token yes is, that's the score of this response. And then that you can signal, you can use for reinforcement learning or whatever you want. So the previous approach does not use chain of thought though, right? You're just asking it is correct or wrong. But you can also incorporate chain of thought. So LLM judges have been shown to benefit if they are asked to generate chain of thought before generating the final score. So can we include chain of thoughts in these LLMs while training the LLM as judge? So what would be the input to the model? The input will be the prompt, the response, and the string let's verify step by step. And you will train the LLM to generate the step-by-step verification string, whatever. So we assume that the step-by-step verification string comes from somewhere, and you will train the model to generate that step-by-step verification string, and also you will train it to generate whether the final answer was correct or not incorrect. And when you do inference, you will again first generate the step-by-step verification, and then look at the log probability of the yes or no token to give a score to the response. And this is how the prompt for chain of thought verification looks like. Okay, so I think I will stop this at this point, because this covers the reward model training aspect of RL. And the next we will in the next class we will see how the reward model can be used in different ways.